You can't run a modern OS, even an RTOS like FreeRTOS, so you can't make an operating system on a microcontroller. Well, that's what everyone told me. That's what people believe. That's what everyone believes. Given these assumptions, I had no choice but to make our own OS. The project goal is to simplify code writing and application writing. And in order to do that, I had a lot of groundwork to do. Microcontrollers have some issue. Basically, code writing is unique to a microcontroller. It is unique because the hardware itself is quite unique for every microcontroller. You can't write a driver that is working for all microcontrollers. Very often, they are uniquely tuned for a particular one. So we had to abstract the hardware from the application level. KRT, or kernel real-time, is a real-time operating system, but basically a scheduler and a real-time tasks. It supports 4, 20, 100 milliseconds and 1 second tasks. It supports up to 255 basic commands. They run in two contexts, real-time or scheduled. The real-time context runs inside an interrupt, and the scheduled context is a stack of tasks which run on 4 milliseconds, 20 milli, 100 milli, 1 second. Because I was challenged by a colleague while learning to fly. He told me I will use the Arduino board and make much faster than you can a custom timer for VFR flight. And I had to use a different board to make it. In the end, I built what is now KRT, the embedded scheduler and real-time kind of operating system. It's a tiny operating system basically. So it runs in an interrupt context for the real-time and the scheduler context. Scheduled tasks are put in the stack. On average, they run the right cycle time, but they can be delayed when the running function before them takes long time. The kernel talks through a serial link with the host. The host is a C++ application embedding a web server. It has an interface with the microcontroller and an interface with application. Applications are built in HTML and JavaScript. They can run on Python, C or C++ external library, Rust, Bash, shell scripts through piping, or control via the UDP sockets, Unix sockets. The host has an interface with the microcontroller, and it has an interface with anything that we want to interface the microcontroller with. And the default is embedding the HTML server so that we can make our UI on a HTML page. We need to write the JavaScript according to the API, and the HTML embeds the application we want to build. There are kernel commands. These allow to run and stop the kernel and use space. In this context, the kernel is really the scheduler and core drivers, but the user application is all peripherals and most of the drivers to control the GPIO, the peripherals, the serial communication, the clock, anything relative to the microcontroller hardware. But this is the kernel and user space embedded core. It is not the same as end user application. So there is a distinction between kernel, user, and end user application. The end user application doesn't run on the microcontroller. Although it can, there are provisions for user specific functions. The kernel supports tools like systats, fault, alarm words, status. We have all the commands relative to the GPIO, analog inputs, digital inputs, outputs, PWM configuration, reading and writings to the port. We can send frames, read frames, and we have CRC. We have provision for a clock, a real-time clock. This project can work for a remote application. It can work from home application. It can work embedded on a simulator. I don't know all the applications that this project supports. So it has become like a framework. And some of these are GPL for this reason. These functions are used by the middleware, that is the host application. And the host allows the external end-user application to use this API and to control the microcontroller in a uniform way. So any microcontroller which implements the KRT kernel and all these functions will support the application that follows the same API. So that the application can be written once in HTML, JavaScript, Python or any other language we want. And then we have to find a port of the kernel for the microcontroller we want to target and run the same application for the new target microcontroller. The KRT kernel for PIC16F628 is functional. It uses 1.5K of flash and 92 bytes of SRAM. The base application is to read and write the GPIO, configure them as an input or an output, set up the port B pull-ups, and the next port we are working on is the Arduino R4 Minima. Once the port is available, any kind of a user application can be built, for example reading the analog voltage, recording minimum, maximum, making calculations such as RLC meter, like for a bench instrument. We can use it as a logger so that we read some values from instruments wired to the Arduino board. And the host application makes a recording, statistics, save files, so it will do the high-level work, so that we have now a direct bridge from the low-level electronics to the high-level. Java code is write once, run anywhere. And this is a similar design, let's say. Once you have your application or your set of applications, they run on the simulator, they run on Arduino, on a Pi. You can now build a custom hardware and embed the same application for it. Unfortunately, we have to write this only once. Now we want the same application to run on a Raspberry Pi, for example. Then we find the kernel that runs the Raspberry Pi, and we just have ported our application to a Pi. But it doesn't need to run Linux. All it needs is the application layer, that is KRT. KRT can act as a minimal operating system, but it can run also as an application. Mostly KRT is written in C, and the Studio code is a C++ application. The Studio interface allows much more than this. It embeds a manual, a platform for sharing application. It is a platform for hosting new applications that we can build ourselves. We can also grab an application from someone else and put inside. It's an integrated environment. Once it is running, it listens to the TCP port as a web server. It is the bridge from application to the MCU. There is a console version and a UI version. We connect through the local host. Now that templates are complete, what we need are ports and end-user applications. That is, your own works are now what really matters for this project. The website link below gives all the information needed to be started up. You can also subscribe and let know in comments any questions you have on this project.